Well, this example may not look like the theorems we've talked about will apply to this, but we'll show how, in fact, they will. Let's show that this equation, x equals cosine x, has a solution in this interval. So some value of x in this interval will make this a true statement. And I think we already know that that's true because cosine, let's see, it crosses at pi over 2. That'd be pi over 2. That's what cosine looks like from 0 to pi over 2. And the graph of y equals x looks like that. So there's a solution. There's some x naught where the two of those graphs intersect, which means this equation is true. All right, well, what do we want to do? We're going to say let h of x equal x minus cosine x. All right, and what we're going to do is set that equal to 0 and prove that it has a 0, and we'll find out that that's basically the solution we're looking for. Since h is continuous, and, well, notice that what's h of 0? H of 0 would be 0 minus cosine of 0, which is 1. It's negative 1. And what is h of pi over 2 equal to? H of pi over 2. It would be pi over 2 minus cosine pi over 2. Well, we know what cosine pi over 2 is. That's where it crosses the x-axis. That's a 0. So that's equal to pi over 2. And that's bigger than 0. So on this side, I'm going to write they have opposite signs. And h is continuous. So therefore, it's going to have a 0 in between h and pi over 2. All right, since all of that is true, since that is true, we can say there exists a c that's in between, or somewhere in the interval, actually strictly in between. So in the open interval from pi over 2, such that h of c is equal to 0. That's by Bolzono's theorem. Okay? Well, what does that imply? H of c is, where's h defined? Right here. H of c would be c minus cosine c. That's the cosine of c. And that equals 0. Well, that implies that c is equal to cosine of c. And we're done. So a solution to this, this equals 0 at x equals c, at h of c is equal to 0, and that means that c is equal to cosine of c.